So we're continuing with electrochemical cells. This is number 16. We have an electrochemical cell which consists of the standard hydrogen electrode, which is the SHE electrode, which actually has an E node, a standard reduction potential set at 0, and a copper electrode, which has an E node set at 0, calculated to be 0.34. Okay, so the first question is, write the Nernst equation for the cell. Well, first of all, if I have the cell at standard potentials, okay, standard reduction potentials, well, then I do not need a Nernst equation. However, it's when the concentration of this copper 2+ or this H+ ion that is different than 1 molar, that's when I need a Nernst equation. Now, at the moment, with the E naught values, my copper 2+ is my strongest oxidant, and thus the reduction half reaction is for the copper couple, and my reaction becomes copper 2+ plus 2 electrons goes to copper. And my reduction, the stronger reductant, with of course is on the reductants are on my right hand side of this, and the stronger reductant is my hydrogen, and so the couple H+ hydrogen will undergo oxidation because it has a lower reduction potential, E node, standard reduction potential, and so that is will undergo oxidation, and that's my oxidation half reaction. The net reaction, of course, my global reaction would be E of the copper plus 2 hydrogens gives me copper plus 2 H+. And so my Nernst equation for this cell will be E naught of the cell equals 0.09592 divided by 2 log of H+ divided by copper plus divided by the pressure of hydrogen. I could also get this E of the cell by looking at the reduction potential alone of copper, the reduction potential for the hydrogen, okay, standardized using the Nernst for each, and subtract both to get this E of the cell. You will get the same E cell if you do that, okay? Now, of course, this E of the cell, as you can see, is related to the concentration of H+ and copper, as well as to the pressure of hydrogen. The next question is to calculate the potential when copper 2+ is equal to 2.5 times 10 to the minus 8. So when the copper 2+ is that concentration, I'm simply going to use the Nernst for the overall cell. And of course, like I said, you can get this E cell as well from E of the copper minus E of the hydrogen electrode. The E naught of the cell is E naught reduction minus E naught of the oxidation, which is the E naught of the copper minus E naught of the hydrogen, which is simply also equal to the E naught of the copper, 0.34. So the E of the cell, number crunch, we got the E naught of the cell. We have 2 electrons transferred for the overall cell. We have the hydrogen plus is at 1 molar, which is standard. The pressure is in 1 atmosphere, and just the copper 2+ is now this number in purple. Do the calculation, you get that the E of the cell is a positive number, and therefore when the concentration of copper is 2.5 times 10 to the minus 8, this cell is indeed a galvanic cell, and it is spontaneous as written, and we had seen the overall reaction. Now, always spontaneity is determined by E of the cell and not by E naught of the cell, especially when we have non-standard conditions, and you have to, watch out for that. If now the concentration of copper 2+, which is part C, is equal to 1.6 times 10 to the minus 17, then plug that number into the Nernst expression for the overall reaction, and you will see that E of the cell now is actually negative, which is less than 0. You notice now that E of the cell is negative, less than 0. And when EC of the cell is less than 0, then this reaction is considered non-spontaneous as written. That being said, what happens? This is part C. How do I write the cell in the first case when my concentration of copper was 2.5 times 10 to the minus 8? Well, in that part, this can be written in the form of on my reduction side. So my copper 2 plus copper is on the reduction side. And this is how you will write the overall cell. Don't forget that there's a line between different phases. So between the platinum with the hydrogen gas pumped in, there's a gas, there's a platinum solid, and we put a hydrogen plus, which is an aqueous medium. There's solid lines in there. The salt bridge is a double line. Copper 2 plus is an ion, so you have to have its concentration there, and then a line, and then the copper solid is at the end. Positive, negative for the two poles, and the electron flows as shown, and you have a voltmeter right in the middle there. This is my spontaneous cell in the first case. However, when the overall reaction will be the copper gets oxidized while the hydrogen is getting, the copper, sorry, is getting reduced while the hydrogen is oxidized. Now, in the other case, however, when the concentration of copper was decreased greatly to 10 to the minus 17, now the cell was not spontaneous as written up here. And so what we have to do is reverse the direction, that the copper become reduced, oxidized, and thus on this left-hand side, and let the hydrogen be reduced, and therefore it will go on the right-hand side. Notice a few things. Notice the order. Now, copper solid goes to copper 2 plus. So you always write these in the order as written in the half reaction side. Okay, and now look at this part. The H plus comes before the hydrogen, while here the hydrogen comes before the H plus. Okay, what I'd like you to do, try to get the Nernst equation or the corrected E for the copper. And then the delta E for the cell will be, of course, equal to the E of the copper in this case. However, it will be equal to the minus E of the copper in this case. Try that, and you will get these same equations that you have here. All right. That's number 16. Number 17. And consider the following cell. We have zinc in sulfate ion. We have copper solid in copper sulfate ion solution. And so they're asking you the first part, the current in this cell, what happens to it? You guys tell me, what happens to the current? You all know that the electron flows up here from the anode to the cathode, from the negative pole to the positive pole. What happens from the current? Yes, the current will flow from the positive pole to the negative pole. So the current in the cell exists from the copper electrode, from here. Oh, that makes sense. So the current will exist from the positive pole. Part B flows from the zinc electrode to the copper node. That's the flow of electrons. And has the same direction of the electron flow. No, that is not correct. It has the opposite direction of the electron flow. And it goes from negative to the positive. No, that's the way electrons go, from negative to positive. The current goes from positive to negative, okay? And so the only correct answer is A. It starts and exists from the positive electrode, which is the copper electrode. What about electrons reaching the copper electrode? what happens to these electrons? Once they come here, they reach the copper electrode. Remember when I discussed for you electrochemical cells at the beginning? I said that electrons are never allowed to actually go into the solution. They can reach the copper electrode, but then they get transferred on the surface of the electrode by surface interaction of the copper 2+ ion bumping into the copper solid here, and then the electrons get transferred to this copper 2+ on the surface. So the first part, do they pass into the solutions? No, electrons will never pass into the solution. Are they captured by the copper metal? No, they go onto the copper metal, but they're not captured by it. Okay, the copper metal doesn't pick up those 2 electrons. On the contrary, who picks up the 2 electrons is the copper 2+, because this side, remember, is undergoing reduction. So it's the copper 2+ that picks up the 2 electrons and it becomes copper solid. So no, the copper actually does not pick up the electrons. It has the same direction as the current flow. And of course, you all know that electron flow does not have the same direction of current flow. They are captured by copper 2+. We just said that they are captured by copper 2+, but they are not captured by the copper metal. And so the answer is D. Okay. The zinc 2+ ions, what happens to the zinc 2+ that is here? Remember, what happens on this side is what? Oxidation. What do we mean? What's the half reaction that's taking place? Oxidation is the loss of electrons. So zinc solid is going to lose electrons. So it's going to go to zinc 2+ plus 2 electrons. So the zinc solid starts to deteriorate on this side, and the zinc 2+ on this side, on the oxidation half, starts to increase. So the zinc 2+ captures electrons. No, actually, it does not capture electrons. The zinc solid loses electrons, but this zinc 2+ does not capture them. Actually, the electrons move up here. Okay, they go up. They're not really lost into solution. They start moving up while the zinc 2+ is starting to form. Zinc 2+ are formed. Yes, they are. They pass into the salt bridge? No. Whatever passes in the salt bridge are neutral ions like potassium nitrate or potassium chloride, sodium chloride, or sodium nitrate. The ions that are in the solution do not pass. It's the salt solution, they go out from the salt bridge. So the salt bridge allows ions to come out, but not to go into it. Get accumulated on the electrode. The zinc 2+ remain in solution. They don't go as a solid onto the electrode. Okay, they remain in solution. There is some material that can, if we had taken solubility product constant KSP, there's some material that can react with the zinc solid and form a layer on top, but not the zinc 2+. Okay, so that's my explanation there, and it's written for you on the bottom. So the only correct answer is B. And finally, number 18 from this part or this section. Okay, a cell is associated with 2 half cells. We have the first half cell and the cell 2 here, the half cell. The first half cell is some manganate and manganese and HCl. The other half cell, of course, both are on a platinum wire, is some chromium and chromate, chromium, and HCl. All of them are under non-standard conditions, or the concentration are not standard. They give us the E naught of the manganese and the E naught of the chromium. Then they ask for the cell diagram. Okay, so who's on the oxidation half and who goes on the reduction half? And how do we write the cell diagram? Well, it's a little bit unfortunate that they ask this question first because frankly, I can't tell immediately from the E nods. I'm not allowed to just look at E nod and tell you, oh, manganese has a higher E nod and therefore it will undergo reduction. We're not allowed to say that. The reason is these conditions are not standard. So just based on the E nods, I can't, right away put manganese on the reduction and chromium, which has a lower reduction potential, on the oxidation side. And so what I'm going to do is solve part 4 first, which actually asks you to calculate the potential on the platinum electrode of each half cell. Why do I want that? I want that because once I know the corrected E, then I could really decide if it's going to undergo reduction or oxidation. As you saw in just the last question, when the copper concentration was decreased greatly, at some point that copper had to undergo oxidation and not reduction. Okay, so let's look at this. So in the manganese electrodes, first we're going to balance the equation before I do a Nernst on it and do a corrected E. So manganese goes to manganese plus, I balance the oxygens with water, and then I balance the hydrogens with H plus, and then finally I balance the charge with electrons, and I get a fully balanced half reaction with the manganese. Then I can write the corrected E for this manganese. I could write E, call it E1 for cell 1. You can call it as well E of the manganese couple, or simply E as you wish. I like to just call it EMN, just so I don't have to write anything down. But best it is to write that this is E of this couple, okay? Because this is E of this half reaction. Okay, so E is the corrected reduction potential of this electrode on this half reaction. So this is E naught of the couple plus 0.592 divided by the number of electron transferred for only this half reaction. And this half reaction, guys, regardless of if it's going to undergo reduction or oxidation, you have to write it in the form of a reduction. Log of products divided by reactants, each to its stoichiometry, do not include the water. Yes, you have to include, remember, the H plus. We did that at the beginning. Now solve, substitute in the E naught, substitute in the concentrations, okay, that are given, and get the E, which is the corrected E when the concentration of manganese and the manganate was not 1 molar. Well, if you look at this E naught and you compare it to this E potential, corrected potential, well, you notice that there's actually hardly any difference. This corrected potential is quite similar. Now, that's not always the case, and we saw that in, like I said, in our previous question. These numbers can vary greatly. They don't have to be equal to the E naught. But nonetheless, in this case, it was. Let's look at the chromium couple. And so we have the dichromate on this side, and we have, dichromate here. We have the chromate ion on the product side. Balance the equation. Go ahead, you balance it. We've done this before. You notice that there's 6 electrons transferred. There's also H pluses in this equation. Get the corrected Nernst equation E, because we have different concentration than standard. This is E naught of the couple, 0.092. Now, I want to point this out. This is a plus, and here I have a plus. Remember when we have plus, I might have made a mistake up here. I said products divided by reactants. Watch out, when I have plus, it's reactants divided by product, okay? Because I put a plus sign. If it was really Nernst, it would be minus, and it would be Q, products divided by reactants. It doesn't matter how you write it, just make sure, that the sign is correct and that you put these in the correct way. Okay, so here I have a plus sign, so it's reactants divided by products to the stoichiometry, and the number of electrons is 6, and no, it's not 30, which is 6 times 5, it's only for this half reaction, because this is for the one electrode. This is the corrected E for the electrode, not E of the cell. So notice this, yes, I'm using Nernst to correct for one electrode. Okay, substitute in the concentrations and get the corrected E. So now we notice that again, even here, there's hardly any difference. So these different concentrations did not change my potential much relative to the standard potential. It's still 1.3. So if I now compare the E of the manganese to the E of the chromate, who do you think would undergo oxidation? Yes, the lower E. Who would undergo reduction? Yes, the higher E. So the manganese will be my reduction half, and my chromium will be my oxidation half reaction. So here, that 18.4 was simply to ask what is the potential on each electrode, and we just solved that, and the answer A, 1.056 and 1.3. And it's at this point that I can solve for number 1, which is, to write the cell diagram, because now the cell diagram is determined by the E value, the 1.506, 1.312. And yes, you do notice that they do not change relative to E naught, but they could have changed. Okay. So I'm not going to go through this. This is now still reduction half is my manganese, oxidation half is my chromium. Now we have to multiply the manganese by 6, the chromium by 5 to balance the charge to get my overall global reaction if I was asked for that. Now they did ask you for the cell diagram, and the cell diagram is going to be the chromium undergoes oxidation, so I start with the chromium, and I should put it on a platinum plate because everything electrode, neutral electrode, because everything is in the ionic form. Don't forget to separate the platinum from all the ions by a line. Everything else in here has a comma between it. A lot of times you see that the HCl can have a semicolon. I mean, we're not going to be that detailed, but you might see a comma though too, because the answer here is a comma in your book, but the better is to have a semicolon whenever there's an acid. Put each with its correct concentration. As well, this is not always the case, but usually this is written in the order as in the oxidation half. So it's chromium 3+, so we start with the chromium 3+, then it goes to the chromate on the product side. The HCl, they don't usually write it on product or reactant, so they always put it at the end. Okay. Same with the manganese, so even if I have my H+ on the reactant side, it goes at the end. Clear? As well, these are separated by commas. If you notice 18.1, the answer D would be closest to this real cell, to this solution for the cell diagram, but this is the way you write it in the best form. There's also a minus on the oxidation half for the and plus on the reduction half side. They asked us in 18.2 for the oxidation and reduction half reactions, and here they are in their balanced form. And the global reaction is the addition of both of these once I've multiplied the upper by 6, the lower by 5 to balance the electrons. And look at the answers there. The answer would be B. Finally, I want the electromotive force of the cell. What do we mean by delta EF? Electromotive force is simply the E of the cell. We can also call it delta E, for meaning that I'm taking E of the reduction minus E of the oxidation. And yes, it's not E naught because this is not a standard cell. The reduction was the manganese, which we called it E1 minus E2, was the half reaction for the chromate. Do the subtraction, and indeed you all already know that this is definitely a spontaneous cell, and the answer is C. Okay, as we noticed that delta E is not spontaneous, and so the free energy variation is what number? Okay. Well, we all know, okay, that the cell is not standard, so we have to use delta E when we calculate the free energy. So this is delta G, which is the free energy of this cell, equals minus NF delta E. Remember, the N is the total number of electrons transferred in the overall reaction, so that's 6 times 5, which is 30. Don't forget the minus sign, please. The Faraday's constant is 96,500 joules per mole per volts. That's the units, or coulombs mole. This is actually moles on the bottom. Let me fix that. Okay, so it's coulombs per mole, and again, the number of electrons, you can consider it as a number of moles of electrons, so the moles cancel. If I multiply by the volts, which is the delta E here, which we just solved of the overall reaction using the Nernst equation, or you could have also used like E nodes of each of the cells separately. Sorry, E of each of the cells. Remember here, how did we? Yeah, here we use the reduction potential for each of the cell. Now, I just do want to point out something here. I unfortunately cannot use the Nernst equation for the overall cell for this reaction. The reason is there's H plus on both sides, and that the concentration of H plus on both sides are not the same now. If they were, I can use the overall Nernst equation to get this E naught in this delta E in the same way. But whenever there's H plus on both equations, the reduction half and the oxidation half, you really have to do it separately to get the correct delta E for the overall reaction. That was the delta E. Solve for delta G. And now the delta G will be negative in joules, and you have to put it in kilojoules. So my answer is minus 561 kilojoules. I have to put a negative sign here. And what they're saying here, the answer is B. What is this idea of instead of 560? 560 would have been the delta G naught if the reaction was in standard conditions. So slightly different concentration gave me a little bit more energy that I can use. Finally, the equilibrium constant, K. What is it? Okay, so when the cell stops producing electricity, the idea, again, equilibrium, when the cell reaches equilibrium, the cell stops. It doesn't give any energy anymore. There is no forward nor backward reaction. Log Fk is N1, N2, or simply N of the overall reaction, delta E naught, regardless of if it's standard or not. You always use delta E naught divided by 0.592. Again, make sure you memorize these equations on the side, memorize them. They come up all the time. E naught of the cell is E naught reduction minus E naught oxidation, which should have 0.18. Put that in, 0.18, 5 times 6 is 30, and get the log K value, put it 10 to the power, to the K, to this number 91, and find the K. The answer comes out to be B. Okay, and that was the last bit, okay, for this section.